But why? Why do we get to draw that line? Where exactly on the scale from electron to cat does the superposition end and the definite reality begin? At what point does both possibilities at once become just one possibility? Nobody knows. That's the measurement problem. And every attempt to solve it, every serious, technically rigorous attempt, has led to one of a small number of interpretations. Each interpretation preserves the mathematics of quantum mechanics perfectly. Each interpretation makes exactly the same experimental predictions. And each interpretation describes a reality that is in its own way completely and utterly incompatible with the common sense, solid chair, coffee on the table world you experience every day. Let me walk you through the main ones. And as I do, notice how each one strips away another layer of what you thought reality meant. The first interpretation, and still the most widely taught in textbooks, the one most physicists learn first and many never question, is the Copenhagen interpretation. Formulated primarily by Niels Bohr and Werner Heisenberg in the late 1920s, it is, in my view, the most intellectually dishonest solution ever proposed to a serious scientific problem. And I say that with deep respect for Bohr, who was a brilliant man. I argued with him. I sat across from him in conference rooms and watched him gesture and pace and build his arguments, and I thought, this man is extraordinary, and he is wrong. Here's what the Copenhagen interpretation says. It says, the wave function is not a description of physical reality. It is a description of our knowledge, our ability to predict the outcomes of measurements. The wave function is a calculational tool. Before measurement, it's meaningless to ask whether the electron has spin up or spin down, whether the cat is alive or dead. These questions only have answers when a measurement is made. And when a measurement is made, the wave function collapses instantaneously, non-continuously, outside the Schrödinger equation to give a definite result. The act of measurement is a special, fundamental thing. It's the boundary between the quantum world, the world of superpositions and wave functions, and the classical world, the world of definite outcomes, of chairs and cats and results. The measuring apparatus, the observer, the act of looking these things are fundamentally different from the quantum systems they observe. And Bohr said, don't ask what's happening before the measurement. That question is meaningless. The only meaningful questions are about measurement outcomes. This is called the shut up and calculate interpretation by its critics, and I'll be honest with you, I've been one of those critics, because shut up and calculate works perfectly for doing physics. You can calculate the probability of any measurement outcome to as many decimal places as you like. Copenhagen is the best tool we have for doing quantum mechanics, but as a description of reality, as an answer to the question, what is actually happening out there? Copenhagen says, there is no out there. There is no reality independent of measurement. Before you look, there is nothing definite. The universe does not have a state until it is observed. And the question that immediately follows, who is doing the observing? What counts as a measurement? Does a rock count? Does an automated detector? Does it require a conscious mind? Copenhagen waves away. Bohr waves his hands and says you're asking the wrong question. And by the sheer force of his intellectual authority and the social dynamics of the physics community in the 1930s, the question goes away for a generation. But it doesn't go away forever. It can't. Because the question isn't wrong. The question is, if nothing is real until it's observed, what was the universe doing for the 13.8 billion years before there were observers? Bohr has no answer. Copenhagen has no answer. And so we need to look elsewhere. Albert Einstein never accepted quantum mechanics. Not its randomness, not its non-locality, not its refusal to give definite values before measurement. He spent the last 30 years of his life trying to prove that quantum mechanics was incomplete, that there had to be something underneath, some deeper layer of reality, some set of variables we hadn't discovered yet that would restore determinism and locality and common sense to the universe. His most famous attack on quantum mechanics was the EPR paradox, a thought experiment he devised with Boris Podolsky and Nathan Rosen in 1935. It involved two particles that interact and then fly apart, remaining somehow correlated. And Einstein showed that if quantum mechanics was complete, then measuring one particle would instantaneously affect the other, no matter how far apart they were, faster than light, across any distance, without any signal passing between them. Einstein called this spooky action at a distance. And he said, This is obviously wrong. There must be hidden variables, local, realistic, pre-existing values that explain these correlations without any spooky action, without any faster-than-light influences. We just don't know what they are yet. He was wrong. Not about the problem the entanglement correlations are real and they are exactly as he predicted. He was wrong about the conclusion. In 1964, a physicist named John Stuart Bell did something extraordinary. He derived a mathematical inequality, now called Bell's inequality, that would be satisfied by any hidden variable theory, any theory that tries to explain quantum correlations with pre-existing local properties. And then the experimentalists got to work. John Clauser in the 1970s, Alain Aspect in 1982, Anton Zeilinger in a series of increasingly airtight experiments over 3 decades experiments for which he, Aspect, and Clauser won the Nobel Prize in 2022. The result, every single time quantum mechanics is right and Bell's inequality is violated. The correlations between entangled particles are stronger than any local hidden variable theory can explain. The universe violates Bell's inequality, which means, and this is a formal mathematical theorem, not a philosophical speculation, the universe cannot be both local and realistic. Local means things only influence other things through direct, near contact, causes propagate at or below the speed of light. No spooky action at a distance. Realistic means physical systems have definite properties whether or not they are being measured. The electron has a definite spin before you measure it. The cat is alive or dead before you open the box. One of these has to go. You can't have both. Bell proved it. The experiments confirmed it. Einstein was wrong. And now you have to choose. Which one do you give up? If you give up locality, you allow instantaneous influences across arbitrary distances. You have a universe where things that happen here can instantly affect things there, no matter how far away there is. If you give up realism, you have a universe where things don't have definite properties until they're measured, where the electron genuinely doesn't have a spin before you check, where reality, physical, tangible, solid reality is created by the act of observation. There are theories, notably Bohmian mechanics, the pilot wave theory, that give up locality and keep realism. In these theories, there are real particles with real positions, but they're guided by a pilot wave that is itself non-local, instantly responsive to anything anywhere in the universe. These theories reproduce all quantum mechanical predictions. They're technically consistent, but they feel deeply, viscerally wrong to most physicists, including me, because they require this universal, faster-than-light, unobservable wave that exists only to guide particles, and that we can never directly detect. Most physicists give up realism instead. And that brings us to the most radical idea in the history of human thought. In 1957, a young graduate student named Hugh Everett II submitted his doctoral thesis at Princeton. His advisor was John Wheeler, a magnificent physicist, a man of great intellectual courage. And Everett proposed something so radical that Wheeler spent years trying to soften it, to make it more palatable, to find some diplomatic way of presenting it to Bohr and the Copenhagen establishment. There was no diplomatic way. Everett's idea was this: what if we simply take the Schrödinger equation seriously? What if the wave function never collapses? What if the Schrödinger equation, which is deterministic, continuous, perfectly behaved, always describes everything perfectly, without any special collapse process, without any mysterious split between quantum and classical, without any privileged role for observation or measurement? If the Schrödinger equation always holds, then when you measure an electron with spin-up and spin-down superposition, the electron doesn't collapse to one outcome. Instead, the electron, the measuring apparatus, and you all enter a joint superposition. There's a version of you who sees spin-up and a version of you who sees spin-down. Both versions are equally real. Both versions experience a definite outcome. Neither version knows about the other. The wave function doesn't collapse, it branches. Every time a quantum event occurs, every time an electron chooses a path, every time a radioactive atom decays or doesn't, every time any quantum mechanical superposition meets any measuring device, the universe branches. One branch continues with one outcome, another branch continues with the other. Both branches are real. Both branches contain a version of you, a version of the cat, a version of the world. And those branches never interact again. They separate into distinct, parallel, forever isolated realities. This is the many worlds interpretation, and it is either the most terrifying or the most magnificent idea ever proposed, depending on your temperament. Let me tell you why physicists take it seriously. They take it seriously because it requires no special collapse process that violates the Schrödinger equation. It requires no unexplained distinction between quantum and classical, between micro and macro. It requires no privileged role for consciousness or observation. It takes the most successful equation in the history of physics, the Schrödinger equation, and says, this is all there is. This is the whole truth. Everything else follows. The mathematics of many worlds is exact and complete. It makes all the same predictions as Copenhagen. It solves in principle the measurement problem by denying that collapse happens at all, replacing it with branching. But look at what you've bought. Look at what you've paid for this mathematical elegance. You've paid with reality. Not just some of reality, all of it. In many worlds, there are an incomprehensibly vast number of parallel universes. Many worlds advocates prefer to call them branches of the universal wave function, but they function as universes, each one equally real, each one containing a version of you right now in a slightly or massively different situation, making every different choice, experiencing every different quantum outcome. The version of you who got in a terrible car accident this morning and didn't. The version of you who was never born, because the quantum events that led to your parents' meeting went differently. The version of you reading this in a world where the Second World War ended differently, because some quantum fluctuation in a general's brain led to a slightly different decision, which cascaded through history. Every possibility realized, every branch real, an infinity of worlds sprouting from every quantum event, every microsecond, forever. And in none of these worlds is there any solid, single, observer-independent reality. The reality you experience is just one branch, one thread in an incomprehensible cosmic tapestry. Your sense that this moment, this chair, this room is real and definite is just the view from one branch. No more fundamental, no more privileged, no more real than any of the others. I want to tell you about a thought experiment that I find more disturbing than Schrödinger's cat. Much more disturbing, because Schrödinger's cat, for all its strangeness, still involves a cat, not a person. And we can always tell ourselves, maybe cats are different. Maybe animal consciousness is different. Maybe the line between quantum and classical gets drawn somewhere before cats. But Wigner's friend doesn't let you off that hook. Eugene Wigner was a brilliant Hungarian-American physicist, a Nobel laureate, a man of deep seriousness and careful thought. And he proposed the following. His friend goes into a laboratory and measures a quantum system, say, our electron with its superposed spin. Inside the laboratory, the friend makes the measurement and gets a definite result, spin up. From the friend's perspective, the wave function has collapsed. There is a definite answer. Reality has crystallized. But from Wigner's perspective, standing outside the sealed laboratory, unable to see in what has happened, from Wigner's perspective, the laboratory contains his friend and the measuring apparatus and the electron, and all of them are quantum mechanical systems. All of them evolve according to the Schrödinger equation. And if he applies the Schrödinger equation to the whole system, friend, apparatus, electron, he gets a superposition. A superposition of friend C's spin up with electron spin up, and friend C's spin down with electron spin down. From inside the lab, there's a definite answer. From outside the lab, there's a superposition. Both descriptions are valid from the perspective of quantum mechanics. Both are what the Schrödinger equation tells you, and they are completely contradictory. When Wigner opens the lab door and asks his friend, "Did you get a result?" What happens? Does the wave function collapse at that moment? Did it collapse when the friend measured it? Does reality become definite for Wigner when he makes his own measurement? Or did it become definite for his friend already? If the wave function collapsed when the friend measured, then Wigner's quantum mechanical description of the laboratory as a superposition was wrong. The Schrödinger equation failed. If the wave function didn't collapse until Wigner opened the door, then from Wigner's friend's subjective experience of having a definite result, was that experience real? Was the friend, from Wigner's external perspective, in a superposition of having two different definite experiences simultaneously? And if you think this is too abstract in recent years, physicists Daniela Froschiger and Renato Renner extended this thought experiment and proved a theorem showing that if you try to maintain quantum mechanics as complete and universal, You get into a situation where two observers, both following the rules of quantum mechanics perfectly, will make contradictory, irreconcilable predictions about the same physical event. They will both be right from their own perspectives, and their perspectives will fundamentally disagree. This result, published in Nature Communications in 2018, is not a paradox to be resolved. It's a theorem. It says, if quantum mechanics is universally valid, if the Schrödinger equation holds for everything, including observers, then there is no single, consistent, observer-independent account of what happens. Reality differs depending on who's looking, not just apparently, not just epistemically, physically, fundamentally. Different observers have different realities, and both realities are equally valid. If this doesn't bother you, you haven't understood it yet. Sit with it. Let it breathe. Let it undo things. I want to give you one more piece of experimental evidence before we pull all of this together. One more piece of evidence that the act of observation, not just theoretically, not just in thought experiments, but in real laboratories with real equipment and real results, changes physical reality. It's called the quantum Zeno effect, named after the ancient Greek philosopher Zeno, who argued that motion is impossible, that an arrow in flight is always at any given instant stationary, and so it can never actually reach its target. He was wrong about arrows. He turned out to be nearly right about quantum systems. Here's the effect. An unstable quantum system, an atom about to radioactively decay, for instance, has a natural decay rate. Left alone, it will decay with a certain probability per unit time. This is standard, well-understood physics. But watch this. Stop. Just stop whatever you're doing right now. Put down your coffee. Close that other tab. I need you to hear something, and I need you to hear it with your whole mind, not just the part of your brain that skims and nods and pretends it understood, because I'm about to tell you something that every physicist, every philosopher, every person who has ever stared up at the night sky and thought they understood even a little about what's going on has gotten completely, catastrophically, magnificently wrong. And the mistake, the single, elegant, almost embarrassingly simple mistake at the heart of it, doesn't live in some obscure equation hidden in a textbook that only 12 people on Earth have read. No. That would be too convenient, too neat, too safe. This mistake lives inside something you do every single second of every single day. You breathe, you look around, you see the chair you're sitting on, the screen in front of you, the walls, the ceiling, the light pouring through the window. You reach out and touch a surface and feel it push back against your fingertips. And somewhere deep in the machinery of your brain, in that ancient, confident, never second-guessing operating system that runs your entire experience of the universe, you conclude, this is real, this is here, this is solid, this is true. And that conclusion, that automatic, instinctive, feels so obvious it barely counts as thinking conclusion, that might be the greatest error in the history of human cognition. Now, I know what you're thinking. You're thinking, come on, the chair is real. I can sit on it. I can feel it. If I drop a book on my foot, that's real enough for me. And look, I sympathize. I really do. When I was a kid in far Rockaway, Queens, I used to argue with my father about the nature of things. He'd point to a bird on a branch and say, you see that? That bird has a name in a dozen languages. But knowing the name doesn't tell you a single thing about what it is. And that question, what is it really, has haunted me my whole life. What I'm about to walk you through today is not philosophy. It's not mysticism. It's not the kind of hand-waving that makes physicists roll their eyes and pour themselves another drink. This is the real thing. This is quantum mechanics, the measurement problem, the many worlds interpretation, the collapse of the wave function, entanglement, superposition, and the single most devastating implication of all modern physics, an implication so radical that even Einstein refused to accept it until the day he died. The implication that reality, as you understand it, does not exist until someone looks at it. And the mistake, the one physics mistake that opens this entire trap door beneath your feet, is something called the assumption of objective collapse. But we're going to get there. We're going to earn our way there. Because understanding why this is so terrifying requires understanding a series of things that each individually seem reasonable, manageable, almost ordinary. And then, when you put them together, the floor disappears. Are you still with me? Good. Then let's start at the beginning, the real beginning. Let me take you back to the year 1900. Not because I enjoy history, I find most history terribly dull, honestly, but because what happened in 1900 is the moment the universe first whispered to us that something was wrong. Physics in 1899 was confident, and I want you to feel that confidence, really feel it, because it's the kind of confidence that comes right before a spectacular fall. The physicists of the 19th century, Maxwell, Boltzmann, Kelvin, the whole luminous crowd had done something extraordinary. They had taken Newton's mechanics, welded it to electricity and magnetism, mixed in thermodynamics, and produced a picture of the universe so complete, so internally consistent, so staggeringly powerful, that Lord Kelvin himself reportedly said that physics was essentially finished. There were just two small dark clouds on the horizon. Two small clouds. The first dark cloud was the strange behavior of light specifically, the failure to detect the medium through which light was supposed to travel. The second dark cloud was what they called the ultraviolet catastrophe, a technical problem with how hot objects radiate energy. Specifically, the equations of classical physics predicted that a glowing hot object, a piece of iron heated until it glows, for instance, should emit infinite energy in the ultraviolet range, which is obviously wrong, because if that were true, every warm object in the universe would instantly destroy everything around it with an infinite blast of radiation. Two small clouds. How hard could it be? The first cloud gave us Einstein's special relativity in 1905. The second gave us Max Planck's quantum hypothesis in 1900. And these two small clouds turned out not to be clouds at all. They were hurricanes. Category 5, civilization-altering, everything you thought you knew is wrong hurricanes. Planck's fix for the ultraviolet catastrophe was almost accidental. He wasn't trying to revolutionize physics. He was trying to solve a specific, irritating mathematical problem. And to make the math work, he had to make one tiny assumption that energy isn't continuous, that you can't radiate energy in any amount you like, the way water flows in a continuous stream. Instead, energy comes in discrete little packets, quanta, like coins rather than water. You can have 1 coin or 2 or 20, but you can't have 1.5 coins. Planck himself found this deeply uncomfortable. He spent years trying to find a way to make the universe continuous again, to take back his own discovery. He couldn't. The universe wouldn't let him. Then Einstein took Planck's idea and said, "This isn't just a mathematical trick. Light itself is made of these little packets, photons." And he used this to explain the photoelectric effect, which won him the Nobel Prize. And then Bohr applied it to atoms, and de Broglie applied it to matter itself, saying that electrons, things with actual mass, things we thought were solid particles, also behave like waves. And Heisenberg and Schrödinger built the whole mathematical machinery. And suddenly we had quantum mechanics, and quantum mechanics worked. Oh, how it worked. It predicted the behavior of atoms with a precision that made classical physics look like finger painting. It explained chemistry and solid-state physics and lasers and semiconductors and every single piece of technology that defines the modern world. Your phone runs on quantum mechanics. The chip inside it was designed using quantum mechanical calculations. The screen glowing in front of your face is a testament to the truth of the quantum description of reality. And physicists were delighted. They were thrilled. They slapped each other on the back and said, "Look at this. Look at what we've done." And almost none of them stopped to ask the one question that should have been asked from the very first moment: what does it actually mean? Here's where I need to introduce you to the most important and most terrifying object in all of modern physics. It's called the wave function. And it sounds innocent. It sounds like just a mathematical tool, a useful abstraction, the kind of thing that lives on a blackboard and stays there, safely contained in chalk and symbols. But it isn't contained. That's the whole problem. Let me explain what a wave function is. When you have a quantum mechanical system, an electron, a photon, an atom, or theoretically anything at all, the wave function is a mathematical description of all the possible states that system could be in simultaneously. It's written with the Greek letter psi, psi, and it evolves over time according to the Schrödinger equation. Beautifully, deterministically, perfectly. The Schrödinger equation is as elegant and precise as anything Newton ever wrote. Here's a simple example. Take an electron. An electron has a property called spin. For our purposes, you can think of spin as being like a coin. It can be either up or down. In classical physics, the electron either has spin up or spin down. Period. End of story. Before you measure it, it has one or the other. You just don't know which. Quantum mechanics says something completely different. Quantum mechanics says that before you measure it, the electron doesn't have spin up or spin down. It has spin up and spin down simultaneously, both at once. It exists in what we call a superposition, a combination of both states, each with a certain probability amplitude. The wave function contains both possibilities perfectly overlaid on each other, as real as each other. And then you measure it. And suddenly, instantly, the wave function changes. The electron chooses. It becomes spin up or it becomes spin down with probabilities determined by the amplitudes in the wave function. And from that moment on, it has a definite spin. This process where the wave function goes from both possibilities simultaneously to one definite outcome is called wave function collapse. And here's the mistake. Here's the thing I need you to hold in your mind and never let go of. Nobody knows what causes it. Not, we haven't figured it out yet. Not, we have a good idea but need more data. Physicists have been arguing about this since 1927, nearly 100 years. And there is still no consensus, no agreement, no universally accepted explanation for what actually happens when a quantum system is measured. The measurement problem, why and how the wave function collapses, is the deepest, darkest, most unresolved question in all of physics. And its resolution, each and every proposed resolution, leads to conclusions so bizarre that they make my head swim. And I say that as someone who spent decades making other people's heads swim with bizarre conclusions. Before we go further into the darkness, I want to ground you. I want to give you something concrete to hold on to. Because the wave function and collapse and superposition can sound abstract, can sound like just math, can sound like something that lives in the subatomic world and stays there, safely far away from the chair you're sitting on and the coffee getting cold on your desk. So let me tell you about the double-slit experiment. The double-slit experiment is the most mind-destroying experiment ever performed in the history of science. I am not exaggerating. I am famous for not being given to easy exaggeration. When I say this experiment contains the heart of the quantum mystery, contains it in a form that is impossible to explain, impossible to avoid, and impossible to dismiss, I mean every single word. Here's the setup. You have a source of particles. Let's use electrons. You fire electrons one at a time at a barrier. In the barrier, there are two narrow slits, side by side. Behind the barrier, there's a detector screen like a photographic plate that records where each electron lands. Now, let's think classically. Before we do the experiment, let's predict what should happen. You're firing tiny little balls particles at two slits. Each ball goes through one slit or the other, right? It can't go through both at the same time. And on the screen behind, you'd expect to see two clusters of impacts, one cluster behind the left slit, one cluster behind the right slit. Simple, obvious in the way that chairs are real. Now do the experiment. What you actually see on the screen is not two clusters. What you see is a pattern of alternating bright and dark bands, an interference pattern. The kind of pattern you get when two waves overlap, when the peaks of one wave reinforce the peaks of another and the peaks of one cancel the troughs of another. It's the pattern of waves, not particles. Okay, you think, maybe electrons are waves. Maybe they spread out and each electron goes through both slits simultaneously as a wave and interferes with itself. That's weird, but fine. Waves can do that. Water waves do that. It's still physics. It's still comprehensible. But then, and here I need you to brace yourself, we make a change. We decide we want to know which slit each electron actually goes through. So we put a detector next to each slit, a tiny little measuring device. We don't change anything else. The slits are the same, the source is the same, the detector screen is the same, and the interference pattern disappears. The moment we try to observe which slit the electron goes through, the electron stops behaving like a wave. It goes through one slit or the other, and we get two clusters. The simple classical particles are little balls pattern. The electrons knew we were watching. No, that's not right. That's the human narrative version. The physically accurate version is stranger, the act of measurement. The physical interaction with the detector forced the electron to be in a definite state. The superposition collapsed. And the interference pattern, which required the electron to be in superposition, passing through both slits simultaneously, vanished. Now here's what kills me. Here's the part I've been thinking about since I first truly understood it, and I've never not once been able to make my peace with it. You can do this experiment by sending electrons one at a time, one single electron alone, no other electrons around it. And the interference pattern still builds up slowly, dot by dot, over thousands of electrons, which means each individual electron interferes with itself. Each single electron somehow knows about both slits. Each single electron exists somehow in a superposition of going through the left slit and going through the right slit simultaneously. And the moment you try to check, the moment you interact with it, the moment you gather information about which path it took, it stops doing this. It picks one. The universe, it seems, behaves differently depending on whether it's being observed. I want to let that sink in. Not skim it, not file it under weird quantum stuff, not my problem. Really let it settle into you. The universe behaves differently when it is being observed. What does this mean? What does this say about the nature of reality? That's what we're here to figure out, and the answer is going to shake you. In 1935, Erwin Schrödinger, the same man who wrote the equation that governs the wave function, sat down and wrote a letter. In this letter, he described a thought experiment. He meant it as a reductio ad absurdum. He meant it as a critique of quantum mechanics, a way of showing that the Copenhagen interpretation of quantum mechanics, taken to its logical conclusion, produces obvious nonsense. He was wrong about the obvious nonsense part, but he was right about the logical conclusion. Here is the thought experiment. You take a cat. You put the cat in a sealed box. Inside the box, along with the cat, you place a tiny piece of radioactive material, a Geiger counter, a vial of poison, and a mechanism. If the Geiger counter detects a radioactive decay event, it triggers the mechanism, which breaks the vial, which releases the poison, which kills the cat. The radioactive decay is a quantum event. It's governed by the wave function. At any given moment, the atom either has decayed or it hasn't. And until you measure it, quantum mechanics says it's in a superposition, both decayed and not decayed simultaneously. Now, the Geiger counter is connected to the atom. The mechanism is connected to the Geiger counter. The vial is connected to the mechanism. The cat is connected to the vial. If we take quantum mechanics seriously, if we take the superposition of the atom and allow it to propagate through the whole chain, then after an hour, the atom is in a superposition. The Geiger counter has detected a decay and hasn't detected a decay. The mechanism has triggered and hasn't triggered. The vial is broken and isn't broken. The poison has been released and hasn't been released. And the cat is alive and dead, simultaneously. In a superposition, until you open the box and look. Schrödinger thought this was absurd. Clearly, you'd say the cat is either alive or dead. Cats don't exist in superpositions. Superpositions are for electrons, for subatomic particles, not for cats. If you measure the atom, check its state repeatedly and rapidly, the act of measurement slows down the decay. If you check it fast enough, if you measure it continuously, in the limit the atom never decays at all. Watching the atom over and over keeps it frozen in its undecayed state. The moment you stop watching, it starts decaying again. This has been demonstrated experimentally. It is real, it happens, and the mechanism is exactly what quantum mechanics predicts. Each measurement collapses the wave function back to the undecayed state, or confirms it as undecayed, restarting the clock, preventing the superposition from evolving toward decay. The act of observation, the physical interaction that constitutes a measurement, holds the universe in place, stops quantum evolution in its tracks, keeps the atom from doing what it would naturally do if you weren't looking. The universe changes its behavior because it's being observed, not metaphorically, not approximately, exactly, measurably, reproducibly in laboratories around the world. By now you might be thinking, okay, fine. Quantum mechanics is strange, the measurement problem is unsolved. But there's something called decoherence, right? I've heard that decoherence explains why we don't see quantum superpositions in everyday life. Doesn't decoherence solve all of this? Almost. Tantalizingly, frustratingly, almost. Decoherence is real, it's important, it's one of the great insights of 20th century physics. And it doesn't solve the measurement problem. Let me tell you why. Quantum superpositions are fragile. An electron in a superposition of spin up and spin down maintains that superposition only as long as it doesn't interact with anything else. The moment it starts interacting with its environment, with air molecules, with photons, with the electromagnetic field, the superposition becomes entangled with the environment. The electron's quantum state and the environment's quantum state become correlated. And once that happens, the two branches of the superposition spin up and spin down become correlated with two different, enormously complex states of the entire environment. States involving trillions of particles, each one slightly differently distributed, each one carrying slightly different information about the electron's spin. And these two environmental states are so different, so orthogonal, in the technical sense that any interference between the two branches of the electron's superposition becomes, for all practical purposes, zero. This is decoherence, and it happens with stunning speed. A dust particle interacting with air molecules decoheres in about 1031 seconds, much shorter than a blink of an eye, much shorter than a vibration of an atom, essentially instantaneous on any scale that matters for everyday life. So after decoherence, the spin-up branch and the spin-down branch can no longer interfere with each other. They behave from a practical perspective exactly like two classical possibilities. The electron is either spin up or spin down, with the appropriate probabilities. Do you see why this seems to solve the measurement problem? It makes the quantum superposition invisible. After decoherence, you can't tell by any local measurement that the electron was ever in a superposition. It just looks like a classical probability. But look more carefully. Decoherence explains why we can't observe the superposition anymore. It does not explain why one outcome is realized and the other is not. After decoherence, you still have, according to the Schrödinger equation, two branches. They're just no longer interfering. In many worlds, both branches are still real. In Copenhagen, you still need a separate collapse rule to pick one. Decoherence doesn't tell you which branch you end up in. It doesn't tell you why there's one outcome instead of two. Decoherence hides the problem. It does not solve it. Carlo Rovelli, one of the most creative physicists alive today, proposed an interpretation called relational quantum mechanics that I find both profound and deeply unsettling. It is in some ways the most radical of all. Rovelli says the wave function is not a property of a physical system in itself. It is a property of a system relative to another system. There is no absolute observer-independent quantum state. The state of an electron is only defined relative to something else, another particle, an apparatus, an observer. Different observers can have different, equally valid descriptions of the same quantum system. And these descriptions can be contradictory. This is not a bug in the theory. It is the feature. It is the nature of reality. In relational quantum mechanics, there are no absolute facts about quantum systems. Every fact is relative to the observer or system that has interacted with the quantum system and become correlated with it. My fact and your fact can differ, and both are equally real relative to each of us. What this means, and I want you to really hear this, is that there is no God's eye view of the universe. There is no cosmic vantage point from which the state of everything can be described simultaneously and consistently. The universe has no single, total, consistent description. It is made of relationships, of correlations, of facts relative to observers. There is no absolute reality underlying it all. Just a vast, intricate, beautiful web of relative facts. Each one real from some perspective, none of them real from all perspectives. This is not mysticism. This is the conclusion of a technically rigorous, internally consistent interpretation of quantum mechanics defended by serious physicists in peer-reviewed journals. The universe is a collection of relationships, not things, relationships. And if there are no things, only relationships between systems, then the solid, independent, observer-independent reality you experience every day is a convenient illusion, a useful story, a practical approximation that works beautifully at human scales but has no deeper foundation. What is the chair you're sitting on, if not an absolute, independently existing object? What is anything? John Wheeler, the man who coined the terms black hole and wormhole and quantum foam, the man who was Bohr's collaborator and Feynman's thesis advisor, the man who thought more carefully about the foundations of physics than almost anyone in the 20th century, spent the last decades of his life developing an idea he called the participatory universe. Wheeler's idea grew directly out of the quantum mechanical observer problem. And it is this: the universe is not a machine that runs independently, with observers sitting outside it and watching passively. The universe requires observers to exist, not just to observe to bring into being. We do not merely discover a pre-existing reality. We participate in creating it. Wheeler was fond of a version of the double-slit experiment done with photons from distant quasars' light that has traveled billions of years across the universe. In a delayed choice version of the experiment, you can decide, after the photon has already traveled most of its journey, whether to set up your apparatus to detect which path the photon took or to observe the interference pattern, and your choice made now, in the present, determines what the photon was doing billions of years ago. Not what you know about what it was doing, what it actually did. The photon's past behavior is determined by a present measurement, retroactively, across billions of years. Wheeler's conclusion: we are participators in bringing into being not only the near and here, but the far away and long ago. The universe, in Wheeler's view, is not a machine. It is a vast self-referential loop. Observers emerge from the universe. Observers make measurements. Measurements bring facts into existence. Facts constitute the universe. The universe produces observers, and the loop closes. We are not spectators, we are co-creators, not in the mushy, metaphorical, motivational poster sense. In the rigorous, experimental, mathematically precise sense, the universe needs us to be real. And if that's right, if the universe needs observers to collapse wave functions, to bring definite facts into existence, to constitute reality, then the question becomes, what happened before there were observers? What was the universe doing for the first 300,000 years before the first atoms formed, the first billion years before the first stars, the first 10 billion years before the first life? Was none of it real? Was it all in superposition, an incomprehensible quantum fog, a Schrodinger's universe waiting for observers to open the box? Or did it somehow observe itself? Did quantum fluctuations in the early universe count as measurements? Does a rock count as an observer? Does a virus? Nobody knows. Wheeler had ideas. They were beautiful and strange and unproven, and the question remains open. I need to be careful here. I need to put up a sign that says, "Here be speculations." What I'm about to describe is not established physics. It is on the frontier, the wild, contested, exciting, possibly crazy frontier of what physicists and philosophers are thinking about. I include it not because I'm certain it's right, but because it follows naturally from the questions we've raised, and because it's too important and too fascinating to ignore. The hard problem of consciousness, as philosopher David Chalmers formulated it, is this: why is there subjective experience at all? Why, when physical processes happen in your brain, is there something it is like to be you? Why isn't it all just information processing, neurons firing, signals propagating, dark machinery with no one inside? Physics in its standard form has no answer to this. The standard picture of the universe is made of particles and fields, governed by equations, and consciousness doesn't appear anywhere in those equations. It's left over, unexplained. The easy problems of consciousness, how the brain processes information, how it integrates sensory data, how it produces behavior, are hard but tractable. But why there's an experience of all this, why there's a you inside reading these words and finding them interesting or boring or unsettling, that's the hard problem. Now, what if consciousness' subjective experience, the observer, is precisely what causes wave function collapse? This is the consciousness causes collapse hypothesis, associated with John von Neumann, Eugene Wigner, and later elaborated by Roger Penrose and Stuart Hameroff. Von Neumann, in his rigorous mathematical formulation of quantum mechanics, showed that the collapse of the wave function can always be pushed further and further up the chain of measuring devices and environments. In principle, you can keep quantizing more and more of the measuring apparatus, treating more and more of the world as quantum, until you reach the very edge of consciousness. And there, he suggested, is where the buck stops. Consciousness, subjective experience, is what cannot be quantized. Consciousness is what collapses the wave function. If this is right, and I emphasize, this is speculative. It is controversial. It is not mainstream. But it is also not obviously wrong, and some very serious physicists have defended it, then consciousness is not an accident of evolution. It is not a side effect of information processing. It is a fundamental feature of the universe, woven into its very physics. The observer is not separate from the universe. The observer is the mechanism by which the universe becomes real. You, your subjective experience, your inner life, the feeling of reading these words right now might be the very thing that collapses quantum superpositions, that selects realities, that makes facts determinate. Your consciousness might not just be witnessing the universe, it might be creating it. I'm going to let that sit there for a moment. We've come a long way, from classical confidence to quantum strangeness, from the double-slit experiment to Schrodinger's cat to Wigner's friend to many worlds to relational quantum mechanics to the participatory universe. And I've been promising you since the very first sentence that all of this hangs on one physics mistake, one single specific mistake. Not a calculation error, not a wrong equation, a mistake in how we set up the problem in the first place. Here it is. The mistake is the assumption so deep, so automatic, so completely invisible that most physicists never notice they're making it, that quantum mechanics applies to the thing being measured, but not to the measuring system. This is the assumption behind Copenhagen. The world is divided into two, the quantum realm, where wave functions and superpositions and uncertainty reign, and the classical realm, where measuring devices and observers and definite outcomes live. The classical realm interacts with the quantum realm through measurement, and measurement causes collapse, clean, sharp, done. But this division, this Heisenberg cut between quantum and classical, is assumed, not derived. It is put in by hand, not predicted by the theory. The theory has no mechanism for specifying where the cut is. It has no way of telling you whether a particular system is quantum or classical. It says, draw the line somewhere, but not, here is where the line goes. And the moment you really ask, with the full force of physics behind the question whether the measuring device itself is quantum mechanical, it is. It's made of atoms. Atoms are quantum mechanical. And whether it should be treated as such, it should, if we're being consistent. The cut dissolves. The line disappears. And you're left with the Schrödinger equation applying everywhere, to everything, all the time, which takes you to many worlds, or to relational quantum mechanics, or to some other interpretation that refuses to make the arbitrary cut. The mistake, in other words, is treating the observer, the measuring system, the classical realm, as fundamentally different from the observed, as existing outside quantum mechanics, as immune to superposition. Because the moment you stop making that mistake, the moment you take the logical step of asking whether the observer is itself a quantum system described by a wave function evolving according to the Schrödinger equation, everything changes. Reality becomes relative, or reality branches, or reality is a web of relationships with no absolute ground, or reality requires consciousness to exist. Every road, once the mistake is corrected, leads somewhere that classical intuition cannot follow. Every road leads to a place where the solid, independent, observer-independent reality we thought we lived in turns out to be something else entirely. Not less, not diminished, but different, stranger, more beautiful in a way that can only be beautiful once you've let go of needing it to be simple. You might be thinking, okay, this is wild, this is fascinating, but so what? If quantum mechanics works, if it predicts experimental outcomes correctly, does it matter which interpretation is right? Does it matter whether many worlds is true, or Copenhagen, or relational quantum mechanics? They all give the same answers. They're all equally good at physics? No, they're not equally good at everything. And yes, it matters. It matters enormously. First, it matters for the foundations of science itself. Science's claim to authority rests on its correspondence with reality, on the idea that its successful theories are telling us true things about how the universe actually is. If the most successful physical theory in history is compatible with interpretations that fundamentally disagree about whether reality exists independently of observation, whether there are parallel universes, whether observers are physically essential to the universe, then we need to know which interpretation is correct before we can say what science has actually taught us about reality. Second, it matters for quantum gravity and the future of physics. The biggest open problem in physics is reconciling quantum mechanics with general relativity. Gravity is described by a smooth, continuous spacetime. Quantum mechanics is described by discrete, probabilistic wave functions. They are fundamentally incompatible in certain regimes near singularities at the Planck scale. And one of the key obstacles to reconciling them is the measurement problem. If we don't know what wave function collapse is, how can we build a theory that incorporates both? Different interpretations suggest different approaches to quantum gravity. Many worlds in particular may have deep connections to the holographic principle and the structure of spacetime itself. Some physicists believe that understanding the measurement problem is prerequisite to everything else. Third, it matters for technology. Quantum computers, quantum cryptography, quantum communication. All of these technologies require us to manipulate quantum superpositions at the macroscopic level, understanding exactly when and how decoherence occurs, exactly what constitutes a measurement, exactly how quantum information behaves under different conditions. All of this requires a deeper understanding of the foundations. The quantum technology revolution of the 21st century will be built on foundations that we have not yet fully understood. And fourth, and this is the one that I think matters most, the one that keeps me up at night, even now it matters for what we mean by us. If the observer plays a fundamental role in quantum mechanics, if measurement is not just an epistemic act but an ontological one, if observation brings facts into existence, if consciousness collapses wave functions, then we are not what we thought we were. We are not passive spectators in a pre-existing universe. We are not tiny, insignificant, accidental creatures on a pale blue dot orbiting a minor star in an unremarkable galaxy. We are participants in the creation of reality. Our acts of observation, our attention, our measurement, our interaction with the quantum world help constitute the universe. The universe needs observers to be real. And we are observers. I find that extraordinary. I find that terrifying and beautiful and true in a way that no purely classical picture of the universe ever was. Let me tell you something I've never been comfortable saying publicly, because physicists aren't supposed to say things like this. Physicists are supposed to shut up and calculate. We're supposed to deal in equations and predictions and experiments, not in the kinds of questions that make you stare at the ceiling at 3 a.m. But I've never been able to shut up, and I don't intend to start now. The deepest question raised by quantum mechanics, the question that I believe will not be resolved in my lifetime, and perhaps not in yours, and perhaps not for centuries, is this. Why does the universe exist such that observation matters? Not how, why? Why is it that the universe is structured, governed by equations, fundamentally probabilistic, shot through with non-locality and entanglement and superposition in such a way that the observer is essential? Why is it that the laws of nature are quantum mechanical rather than classical? Why is it that at the foundations of reality there is irreducible uncertainty, indeterminacy, wave functions that spread and collapse and branch? Classical physics, for all its beauty, described a universe indifferent to observers. The planets would orbit the sun whether anyone was there to see them or not. The apple would fall whether Newton was sitting under the tree or not. Reality was just there, solid, fixed, independent, waiting to be discovered. Quantum mechanics describes something different. A universe that is in some deep sense about observers. A universe whose laws guarantee that observers cannot be entirely separated from what they observe. A universe that might, in Wheeler's vision, need observers to exist at all. Is this a coincidence? Is it an accident that the universe is quantum mechanical, that it has the very structure that makes observation fundamental, and that it also happens to produce complex structures, planets, chemistry, life, minds, observers? Or is there something deeper? Is there a reason why the universe is the kind of place that can ask questions about itself? Is there a reason why a universe composed of quantum fields has evolved to contain entities that can measure quantum fields? Wheeler believed the universe was a self-excited circuit, a giant feedback loop. Reality bringing forth observers, observers bringing forth reality. The universe using physics to bootstrap itself into existence. I don't know if he was right. I know that I cannot prove he was wrong. And I know that the alternative, that it's all a meaningless coincidence, that consciousness and observation just happen to be fundamental to the laws of physics, and this has no deeper significance, feels to me like the least satisfying answer possible. We've come a long way. We started with a chair. We ended with the universe as a self-creating feedback loop. Along the way, we encountered superposition, entanglement, wave function collapse, the double-slit experiment, Schrödinger's cat, Wigner's friend, Bell's theorem, many worlds, relational quantum mechanics, decoherence, the quantum Zeno effect, the delayed choice experiment, and the hard problem of consciousness. And we identified the one physics mistake at the heart of it all, the assumption that the observer lives outside quantum mechanics, that the classical measuring apparatus, the experimenter, the conscious mind, can be cleanly separated from the quantum system under observation. The assumption of objective observer-independent collapse. That assumption is almost certainly wrong. What to replace it with? We don't know yet. That's the honest answer. After nearly 100 years, we genuinely, truly do not know. But here's what I want you to take away from all of this. Not despair. Not nihilism, not the therefore nothing matters conclusion that seems to follow from reality might not be real. Quite the opposite. The fact that reality might not be independent of observation, that the universe might require observers, might be constructed from relationships rather than things, might branch with every quantum event, might be fundamentally different depending on who's looking. This doesn't diminish reality. It elevates the observer. It elevates you. If you are an observer in a universe that requires observers, if your act of looking, your interaction with the quantum world, your conscious experience is not just witnessing reality, but participating in its creation, then you are not small. You are not insignificant. You are not a side effect of chemistry in a universe that doesn't know you exist. You are doing something that the universe needs. I know that sounds grandiose. I know it sounds like exactly the kind of human self-flattery that science is supposed to dismantle. And maybe it is. Maybe consciousness causes collapse is wrong. Maybe many worlds is right, and there's no special role for observers, just a proliferation of branches that all occur regardless of whether anyone's there to see them. Maybe relational quantum mechanics is right, and there are only relative facts, no privileged perspective, no special role for human consciousness specifically. But even in those cases, even if we're not cosmically special, the universe is still stranger and more wonderful than anyone in 1899 could have imagined. It is still a place of breathtaking, vertiginous strangeness, where particles are waves, where observation changes outcomes, where nothing is definite until it is measured, where entangled particles share correlations that no local realistic account can explain. It is still a place that rewards curiosity, that punishes complacency, that opens up into greater strangeness the more carefully you look. And maybe that's enough. Maybe the appropriate response to the quantum world is not the false comfort of, well, at the macro scale it all looks classical, so I don't need to worry about it. Maybe the appropriate response is wonder, real wonder, the kind that doesn't resolve into satisfaction but deepens. I have spent my career telling people that physics is not about what things are ultimately. It's about what they do. It's about prediction, calculation, experiment, the hard-won agreement between theory and measurement. But I lied, or rather I was incomplete. I was so worried about physics being dragged off into metaphysics, into mysticism, into the endless, unresolvable arguments of philosophy that I overcorrected. I said, just calculate. Don't ask what it means. I was wrong. The question of what it means is the most important question there is. What quantum mechanics means is not settled, and the stakes of getting it wrong or worse, of refusing to engage with the question at all, of teaching generation after generation of physicists to calculate beautifully and think shallowly, are enormous. We are in the middle of the greatest conceptual revolution in the history of human thought, greater than Copernicus, greater than Darwin, greater than Einstein, because Einstein's revolution, as radical as it was, still left us with an objective, observer-independent reality, just a curved and relative one. Quantum mechanics takes the further step of putting the observer inside the theory, of making measurement fundamental, of refusing to tell a clean story about what happens when no one is looking. And the physicists who will solve this, who will figure out, once and for all, what quantum mechanics is saying about the nature of reality, are probably not yet born. Or if they are, they're in school right now, learning calculus, reading their first physics textbook, staring up at the night sky and wondering, I want to talk to those people. I want to say, the problem is real, the question is real. Don't let anyone tell you it's been solved, or that it doesn't matter, or that you should just calculate and not ask what it means. The greatest unsolved problem in physics is not dark matter, not quantum gravity, not the cosmological constant. It's the measurement problem. It's the question of why and how. The quantum world gives rise to the classical world, of why and how superpositions become definite outcomes, of what role, if any, the observer plays in this process. It's the question of whether reality is real, and until we answer it, we don't really know where we live. We have this enormous universe around us. We have these extraordinary laws of nature, quantum mechanics, which predicts the behavior of matter with a precision that puts every other science to shame. We have the double-slit experiment and Bell's theorem and entanglement and the quantum Zeno effect and Wigner's friend and delayed choice experiments and all of this extraordinary evidence that the universe is not what we thought it was. And we have this mystery, this deep, unresolved, 100-year-old mystery at the heart of the most successful physical theory ever developed. A mystery that tells us at minimum that the simple, solid, observer-independent reality of common sense is not the whole story. And at maximum, it tells us that the universe is a self-creating dream and we are the dreamers. I don't know which it is, nobody does. But doesn't that make you want to find out? Because that's the thing about the deepest mysteries. They don't make you feel small. They don't make you want to give up and go home. They make you want to lean in. They make you want to think harder, look closer, ask better questions. They make you feel alive. And if that's the only thing you take from this, if you walk away from this conversation, not with answers, but with better questions, then I've done my job. The universe is strange, stranger than we can currently imagine, stranger probably than we can imagine, with the cognitive equipment evolution has given us, evolved to model mid-range objects moving at everyday speeds in everyday gravitational fields, not quantum fields and superpositions and entangled particles separated by light years. But we keep trying. That's what humans do. We keep looking. We keep measuring. We keep building better theories and better experiments and asking better questions. We don't stop at the edge of the comfortable and say, good enough. We lean out over the abyss and look down. And the universe, quantum mechanical, strange, non-local, observer-dependent, maybe branching, maybe relational, maybe participatory, looks back. What does it see? That's the question that will occupy the best minds of the next century. I hope one of them is you.